Hi, I'm William Webb. I'd like to talk a while about the blending special relativity and the nuclei. This is the third of a series of documents, videos that I presented. The first was blending special relativity into atoms. The second was blending special relativity into optics. And the third is blending special relativity into nuclei. The problem presented in this video is that physics teaches that nuclei are a cluster of little round ball protons and neutrons that are said to be nucleosynthesized together. And they require a special nuclear strong force to hold them together, to hold themselves together, and a special nuclear weak force to control the emissions that come out of that cluster. The cluster doesn't in any way, shape, or form satisfy special relativity, so a new model is needed. Here's the solution that we have discovered. Nuclei are a threesome of photon-circle quarks that correctly incorporate special relativity to achieve both binding and emissions coming out of the nuclei. So here's a typical threesome of quarks that make up a nucleus. All nucleuses look somewhat like this. Most nucleuses look exactly like this. It's a threesome of quarks. Each one of the quarks is warped from special relativistic warping, so that none of them is the same, has the same radial size as the radial rest size. The quarks are rotating and contracted in size. And the threesome consists of two outside quarks that are always the same size with a positive charge on them, and a center quark with a negative charge. These nuclei constructed in this fashion use normal electrostatic forces to bind the threesome and also to control the production of their emissions. A very nice combination. So here's what a hydrogen atom looks like, just to refresh your memory of the overall structure of an atom. The hydrogen atom, if you look real close, has a proton nucleus, which is a threesome of photon-circle quarks here in the middle, and the hydrogen atom has one photon-circle electron, and this hydrogen atom is shown emitting tangentially emitting a photon circle from the photon-circle electron. When a threesome of quarks called a neutron decays and turns into a proton, this is the way it works. The negative center quark of the neutron delaminates a photon-circle electron and changes its threesome shape to the shape of this proton shown here. And that proton is the proton that you see up here in this hydrogen atom as the nucleus. The structure equation for photon-circle quarks has an interesting feature. The structure equation is simply given by Einstein's two equations, his equation for the energy of a photon divided by his equation for the total mass energy of any matter. Photon-circle quarks are a variety of the photon, and we know that photons can laser, that is to say, they amplify their structure by having two photons occupying the same space at the same time. Photon-circle quarks can do the same thing. They can also synthesize, and it's a very important feature that they have. They use synthesis, for instance, to, here's a figure of a neutronium-1, which is the same as a neutron, the three quarks of the neutronium-1. And here's a synthesized figure of neutronium-A. It has a mass number A times the mass of the neutron. A can be a number like a 2 or 10 or a 75. This neutronium A is the same size and the same shape as neutronium-1. It's just 8 times more massive and has 8 times more charge. The net charge of a neutron and a neutronium A, of course, the total net charge is always equal to 0. The net charge being equal to 0 gives rise to the name neutron. It's neutral in charge. It's interesting to look at the ratio of the charge on the outside quark to the central, either one of the outside quarks to the central quark. For the neutron, that ratio, the absolute value of that ratio, the outside quark charge to the center quark charge, for all the neutroniums has a value of 0.5. When the center quark of the neutron decays and emits an electron, or multiple number of electrons, the quark charge ratio changes and increases in accord with this equation. This figure illustrates the electrostatic forces that bind a threesome of photon-circle quarks. The two outside quarks both have the positive charges, so they repel one another. The center quark is attracted to either one of the outside quarks, the center quark having electric charge different than the outside quarks. It's determined that the repulsive force is given by this equation and the attractive force is given by that equation. And when those two forces are equal, that gives rise to this equation of balance for the threesome of quarks. The equation of balance is used extensively in computations for quarks. Well, we know for the neutron, we know the quark charge ratio, that being 0.5, so we could plug 0.5 into this equation and immediately determine that the neutron's outside quarks have a spatial angle of warpage of 30 degrees, and the center quark of the neutron has a spatial angle of warpage 60 degrees. The neutrons and the neutronium A's all kind of have a side profile looking like a stack of pancakes with an hourglass profile. Photon-circle quarks in a nucleus use de-warping to produce decay emissions. Decay emissions typically being emissions of a photon-circle electron or emission of a photon-circle positron, or a combination of both. And this figure is used to determine the forces, the electrostatic forces that are causing the decay emission. The two most important forces causing emissions are the center quark's self-tension and its outward attraction. The center quark is attracted to both of these two outside quarks, that outward attraction being the major force of the two forces. There's also a third force, the centrifugal force of the center quark, but the centrifugal force is determined to be quite small, and so it's normally not included in the calculations of emissions. The center quark can free itself of these forces simply by emitting a photon-circle electron, and it does so with the electrostatic forces being the cause of that emission. Earlier on the previous page, we talked about the attractive force binding the threesomes of quarks, and that attractive force is graphed here. It is a bell-shaped curve, somewhat bell-shaped curve. And the neat part about it from calculus, so we find out that the maximum of that attractive force occurs at an angle of 35.26 degrees, and that becomes an extremely important angle in nuclear physics. Here's an experiment you can do. 35.26 degrees is the same as the angle whose tangent is 1 over the square root of 2. And if we use the balance equation to determine what the quark charge ratio is that relates to 35.26 degrees, we get a charge ratio of 0.77. That charge ratio is used in conjunction with the old-fashioned chart of the nucleids. Every school in our country has a chart of nucleids somewhere hanging on a physics or chemistry wall. And we can use that charge ratio in conjunction with this chart of nucleids to, for the first time ever, calculate the slope of the chart of the nucleids. And that slope turns out to be given by this equation, the n being the number of assumed neutrons in the nucleus, z being the number of assumed protons in the nucleus. So this old-fashioned chart's slope can be calculated, and that line of demarcation is shown to properly segregate 74 electron emitting nuclei, shown in green here. It segregates 57 electron captors or positron emitters, shown by black X's down here. And it properly locates 27 stable nuclei, shown by the little red spots. That's 160 total experimental points that are properly segregated by this simple equation. The figure below illustrates the what I call natural dewarping decay of the Newtonium-4 nucleus, and it's decaying to a stable helium-4 nuclei. The decay is a especially aggressive decay. It has 4 electrons plus 2 positrons emitted, and what I do is show a picture here of the Newtonium-4, and I fit the illustration of the nucleus with scoreboards to show first the initial charge on each one of the threesome of quarks, the amount of charge loss from each one of those quarks, and the final charge resulting. And for the Newtonium-4 decaying, it's emitting 2 positrons and 4 electrons. The positrons and the electrons, 2 of the positrons and 2 of the electrons annihilate, and the net emission is 2 electrons and 4 gamma rays, photons, gamma photons. The resulting nucleus then is helium-4. It has a spatial angle of warpage of 42.7 degrees, and it has a final quark charge ratio of 1.25, a very high quark charge ratio. I also do similar types of calculations for 5 additional nuclei, Newtonium-1 naturally decaying, Newtonium-2 naturally decaying, Newtonium-3, Newtonium-6, and Newtonium-7 all decaying. They decay to Newtonium-1 decays, of course, to the hydrogen nucleus, the proton. Newtonium-2 goes to the deuteron. Helium-3, lithium-6, and lithium-7 are the other ones. those calculations for the K of those are shown on the following couple pages. And those six are combined with, those six calculations are combined with 21 additional calculations, and I presented the resulting quark charge ratios are presented in this figure here. And those persons who have backgrounds in physics and have studied the nuclear binding energy curve in physics recognize this shape of quark charge ratios being virtually identical to the nuclear binding energy curve. That goes a long way toward confirming that this whole concept is correct. Because the concept is correct, we can use the blending of special relativity in the nuclei to do things like calculating the rest mass energy of quarks. A photon-circle quark for a neutron, for instance, can be inserted into this equation. This is the neutron's assumed measured correct mass. It's not necessarily exactly correct, but close to being correct. The equation for determining the rest mass becomes quite simple. The cosine theta factor is used in two places for the two outside quarks and the center quark. And from that calculation, you get that the rest mass of a photon-circle quark is given by 0.3887 excuse me, times 10 to the minus 27. Well, if that's the rest mass of the quarks, we can calculate the amount of warpage that a neutron typically has, and the rest mass would be 3 times that value. And from the actual measured mass, we determine that the neutron is approximately 70% rest mass and 30% relativistic mass. It's highly warped, and from this you can see the absolute necessity of being able to incorporate special relativity into nuclei. You can also do other things by using the structure equation that we presented back earlier. You can calculate the rest radial size. We calculated for the neutron, and after calculating its rest size, we can then calculate its warp size, and it's found that that warp size agrees quite well with the measured mass for the neutron, 1.37 versus 1.56. That's a fairly reasonable measurement and calculation. So photon-circle science has provided us with the knowledge to calculate all the properties of nuclei if we want to spend the time and the effort to do so. It's very useful to do so. In summary, nuclei are a threesome of photon-circle quarks, and they employ special relativistic warping to achieve nuclear binding and nuclear emissions. And there's no requirement for a nuclear strong force or a nuclear weak force, just normal electrostatic forces to do the binding and normal electrostatic forces to control production of the emissions. Photon-circle quarks are a variety of photons so they can synthesize. Photon-circle quarks dewarp to produce decay emissions, and their math has been shown to drive the slope of the chart of the nucleons. Photon-circle quark charge ratio is is found to correctly define the shape of the nuclear binding energy curve, an extremely important discovery. And so we have found that the photon-circle has a blend of special relativity into nuclei and provides us with the knowledge to calculate all the nuclear properties. For mathematics of the whole process, the detailed mathematics, you can contact me. I'd also like you to review the blending of special relativity into atoms and the blending of special relativity into optics. Thank you.